Hello guys, my name is Richard. It has never changed. Welcome back to my YouTube channel. So today we are tackling the chapter 6 of the MCAT chemistry review, the topic chemical equilibrium. Now let me paint this scenario for you. Imagine you've made it through your medical school. You are now doing your residency rotation and you are doing pediatrics. And then you are on a call. So you got a call, and when you got there they gave you that the code that the kid have is DKA, which is diabetes ketoacidosis. Now diabetes ketoacidosis is a disease or a condition most of you have heard before, where there is like a production of ketone acids in the blood. Now you look at the child, and the child was hyperventilating, and then you ask your nurse or whoever is assisting you that why is the child hyperventilating, and the nurse or your assistant wrote you this equation: carbon dioxide plus water in a reversible reaction producing hydrogen bicarbonate, and it dissociates into hydrogen ions and then the bicarbonate ions right in the aqueous solution. So then you look at your assistant and then you're like, why are you giving me this equation? Then it dawns on you that it is the Châtelier's principle. Now, I'm not a French person, so the pronunciation, I might have butchered it. Châtelier's principle. You realize that the child is hyperventilating because the child is trying to blow off more carbon dioxide of the system. Now, if the child blows out more carbon dioxide in the system, he takes products, he takes some reactant out of the system. And by taking the reactant out of the system, the Châtelier's principles suggest that the equilibrium of this reaction would shift so that more reactants are being produced. Whatever you take away from the system, the equilibrium shifts, that thing that you take away, more of it is being produced in the system. So you take CO2 from the system, the equilibrium will shift to left, and by so doing, the hydrogen ions and then the bicarbonate ions in the blood would react to form hydrogen bicarbonate, which in turn would react to form more carbon dioxide, which will react to form more carbon dioxide and then water, and keeps on the child will keep on hyperventilating until there is like a more stable version of this equation. Now this equation is called the bicarbonate buffer equation, and it is very important because this is how carbon dioxide is taken out of the blood, and this is also how the blood maintains its normal pH of around 7.3. With that being said, let's move on to our topic, chemical equilibrium. So when we talk about chemical equilibrium, what we are basically saying is that what is the midpoint of the reaction, right? That is a question that you ask yourself. What is the midpoint of the reaction? And if you remember our last chapter, the chapter 5, we talked about chemical kinetics, which talked about rates, how fast the reactions do occur. Now the chemical equilibrium is the midpoint of these chemical reactions. The product we do form from those irreversible reactions will depend on our limiting reagent. So the limiting reagent will determine the amount of product that we do form. Let's move on to dynamic equilibrium and reversibility. Now, when we talk about dynamic equilibrium, what we are saying over here is that the concentration of your reactants and the concentration of your product will be in a dynamic equivalence. Meaning it in a dynamic equivalence does not mean they are equal. It means it is at a point where the concentration of reactants is stable enough to keep on producing products, and the concentration of products also stable enough to reverse back into a reaction, into the reactants. Now let me visually present it to you visually. let's say we have this our x and y plane, and we have our concentration, that is the percentage of concentration over here, and then this, we look at the experiment over a time t. Right now, I'm gonna use this red ink as this red pen as my uh product, and I'll use this blue as my reactant. Now will start with a certain concentration of reactants, which will be over here. So this y value is my certain concentration of reactants that I do start with. And these reactants could be whatever is combining to form it. That's not necessarily has to be just one substance. Could be 2, 3, 4, how many ever you're trying to combine. Now, as soon as I start reacting, right, my concentration of reactants are going to reduce, right? Now, once my concentration of reactants starts reducing, I'm going to start forming what we call products. So there is no product when I first started with, but as soon as I start reacting, products are going to be formed, right? And if it was an irreversible reaction, this reaction will come to a completion over here, like directly to a completion at some time where the concentration of the reactant are going to be 0, and then the concentration of my product are going to go further up, right, where it's going to be also maximum, right? This is an irreversible reaction. So the red ink is my concentration of products, and my blue ink is my concentration of reactants. The reactant will decrease to 0. The concentration will be gone. The product concentration is going to be at a maximum value. Now, it doesn't necessarily mean it's going to be the concentration of the reactant you started with, because you got to consider your stoichiometry ratios and coefficients when dealing with something. But when we talk about dynamic equilibrium, right, what we're talking about is that although when I start reacting, the concentration of my reactant are going to be reduced, now it's going to get to a certain point where there will be no more reduction in the concentration of the reactant. So it is going to plateau somewhere over here. Now, once it has plateaued somewhere over here, my concentration of the product are also not going to continue all the way to its maximum. It is also going to what? Plateau somewhere over here. Now I'll get something like this, right, where this over here is my product, and then this over here is my reactant, right? And by so doing, I have attained what we call and by so doing I have attained what we call dynamic equilibrium. Means with this dynamic equilibrium, if I'm supposed to add more products to this system, if I'm supposed to add more reactants to this system, right, like I increase the concentration of reactants in this system over here, right, the equilibrium is also going to shift so that I'll produce more product in this system over here too, right, more product. So it's going to go all the way up and then plateau over there. And the point of intersection between the reactants and then the product is what we call equilibrium point or equivalent point. Over here is what we call the equilibrium point. Now, when the system attains this equilibrium, right, so let's trace over here. When the system attains this dynamic equilibrium, right, it does not also necessarily mean that the concentration of the reactants is equals to the concentration of the product. As you see, the concentration of the product over here is a little bit higher than the concentration of the reactant, which is also what? Down here. So if I attain, this is what we call dynamic equilibrium, and then it only occurs in reversible reactions. So reversible reactions is when the reaction can go forward to produce your products, but those products can also combine and come back to produce their reactants. So from here, let's move on something that we call the law of mass action. Let me come over here and let's do it. Law of mass action. Now, when we talk about the law of mass action, what we are talking about is the equilibrium constant of the reaction. So let's consider a generic reaction. So considering this generic reaction, AA plus BB gives me CC plus DD. Right? If I'm to consider this generic reaction and I am tasked to find the law of mass action. Now, the first thing you should know is that the law of mass action is a law, right? And then this law states that at a constant temperature, right, at a constant temperature and pressure of a system at equilibrium, right, this ratio is constant. This ratio is constant. Now we are assuming that this equation is our system, right? This ratio being constant is that the equilibrium constant, which is the K equilibrium, the equilibrium constant is equals to C to the power of C, D to the power of D, all divided by A to the power of A, B to the power of B. Now, if you look at this, critically, you are going to say that at a constant temperature and pressure of a system that is equilibrium, the rate of the reversible reaction over the rate of the forward reaction is constant. But what you should know is that over here, the coefficients, the stoichiometric coefficient that we put on top over here, the dBA, is now equal as the rate. When we was talking about the rate, we talked about what we call the order of the reaction. Now in the rates, we put the order of the reactions up here, but in the equilibrium, we put the stoichiometric coefficients up there. And this equation is always constant, provided this ratio is always constant, provided you keep the system at equilibrium and the temperature is constant and the pressure is constant. The reason why you have to keep the temperature and the pressure of the system constant is that the temperature and then the pressure are going to influence the rate of the reaction. It might act as a catalyst. So if you do influence the rate of the reaction, there is going to be such that maybe more products are going to form or more reactants are going to form, and you're going to shift the equilibrium. So thereby this ratio wouldn't be constant if you do not keep these two items also constant. Now that we have gotten the equilibrium constant of equation, or the law of mass action of a chemical equation, we can also relate the rate of the reactions to this. But just note that the rate law expression is not equal to this. There is a difference between the rate law expression and this one. If you want to know, go watch our previous video on chemical kinetics. Now, how do we create a link between this chemical equilibrium, or the equilibrium constant over here, versus the rate of the reaction? Now let's consider this one-step reaction, right? If we have this one-step reaction, 2A goes to become B plus C. See, this is a decomposition reaction and it's a one-step reaction. The one-step reaction means that it means that this reaction is the actual molecular representation of the reaction. There are no intermediate form. Means this reaction represents the reaction pathway, which is the reaction mechanism of this specific reaction over here. So if it is a one-step reaction and it represents the actual reaction pathway, the reaction mechanism, I could infer that the rate of the forward reaction, right? The rate of the forward reaction is equals to the forward reaction constant, the concentration to this power 2 here. Now I was stressing over it being one step reaction mechanism because of these two. Because if it wasn't one step and this is not the, if it's not one step, this cannot be the actual representation or the reaction path, because then there will be a formation of an intermediate and I couldn't use this to represent the order of the reaction. But since it's a one step, I can use the 2 to represent that as the order of the reaction. So let me come over here. The rate of the reverse reaction is also going to be, the rate of the reverse reaction is going to be K reverse, right? It's going to be B plus B dot C over here, right? Now, I could also say that the rate of the forward reaction is equals to the rate of the reverse reaction. So rate of forward equals to the rate of reverse, right? So over here I can say that this Kf a power 2 is equals to this B Kr over here is equals to this B C up here, right? Now if I divide over, if I want to get the ratio, right, of Kf over Kr, if I want to get a ratio of the Kf over Kr, I am going to get something like A2 divided by B dot C, right? Now from here, let's try to make Kf over Kr the subject over here. So I have Kf, right, into bracket A squared, and I divide by Kr, means I divide here by Kr, I divide here by Kr, Kr will cancel Kr over here, and I'm going to have this one over here, B C over here. Now once I have this, I want to make Kf over Kr the subject. So what I have to do is to multiply all of this side by 1 over the concentration of A, and then multiply this side over 1 over the concentration of A squared here. So this will cancel this, and I'm going to get Kf over Kr is equals to B C all divided by A squared over here. Right, now I have my BC all divided by A squared, and this Kf over Kr is also equals to, that is the rate constant of the forward reaction over the rate constant of the reverse reaction is the equilibrium constant. So this will give me the Keq over there, right? Comprende. Now that we have seen something like this, right? What if we have like multiple step reaction? What if we have like, this was just for a one step reaction. If we have a multiple step reaction, and let's say that the rate for the forward reaction is equals to Kn, right? And then the rate of the reversible reaction, right, is equals to then the rate of the reversible reaction is going to be K minus N. Because if it is forward, it's positive. If we are going backwards, we will take from it, so it's going to be negative. So therefore, my equilibrium constant, like my equilibrium constant of the forward reactions, are going to be my Kf of the forward reactions are going to be like Kn1 plus Kn2 plus Kn3, like how many steps of reaction that I do have till infinity. And my K of the reverse is going to be K minus N1 plus K minus N2 plus K minus N3, all the way till however steps of reaction that I do have. And then we've stated that the Kf over Kr is, like, when we did it, we found out that it became a reciprocal, right? So which is also, so the Keq, which is equals to the Kf over the Kr, is going to be Kn1 Kn1 dot Kn2 dot Kn3, all divided by K minus N1, K minus N2, K minus N3. So that would be the equilibrium constant for if we have a reaction that has multiple steps, and you can calculate the Kf and then the Kn of all of those multiple steps. You could make an inference that if you do the vector multiplication of the forward reaction over the reversible reaction, you are going to get the equilibrium constant. Let's talk about reaction quotient. Before we can talk about reaction quotient, we have to, refresh a little bit about the equilibrium. We said the equilibrium is the point in a chemical reaction where, say the rate of the forward reaction is equal to the rate of the reverse reaction, and the concentration of reactants in it is dynamically equivalent to the concentration of the products. Now, reaction quotient, since equilibrium tells us the midpoint, reaction quotient tells us how far we are away from the midpoint, or how far until we get to the midpoint, right? So with that being said, reaction quotient also still takes on this same equation that we did wrote over here. So the reaction quotient, the QC, still takes on this equation. They are the same exact calculation, right? But then the only difference between the reaction quotient and the equilibrium constant over here is that the equilibrium constant can only be calculated at equilibrium. So you can only calculate this at equilibrium, whilst you can calculate this at any point in the reaction. Whether it's at equilibrium or it's not at equilibrium, you can calculate it at any point in the reaction. Now, once you do calculate a reaction quotient, there are like some few things that you do have to know, because the reaction quotient compares to the equilibrium constant over here. So let's say you do calculate for the reaction quotient, and then you find that the QC is less than the reaction quotient over here. If the QC is less, right, than the reaction quotient, we know that the reaction is not yet at equilibrium, meaning reaction is not yet at equilibrium. It hasn't gotten to the equilibrium point yet. Not yet at equilibrium. And if this is not yet at equilibrium, there are a few things that happens over here, meaning there are more reactants. There are more reactants than products. That is one thing. Whether it's being the concentration of the reactants or the pressure of the reactants, there are more quantity. Whatever quantity you measure the reactants in than the product. That is 1, 2. And then the second one is that the equilibrium constant is going to shift to the right. The equilibrium will shift right. Why would the equilibrium shift right? So that the reaction would favor the forward reaction, so that more product is going to form. So when the equilibrium will shift right, the reaction favors the forward reaction, right? And therefore, once it favors the forward reaction, more products are going to be formed. And once more products are going to be formed, then the equilibrium would come and then attain itself in neutrality. Now, those are the things that it implies when the when the reaction quotient is less than the equilibrium constant. Now you might also do some calculations where your equilibrium constant QC is equals to KEQ. Now when you find that your equilibrium your reaction quotient is equals to the equilibrium constant, the thing that you should know is that the reaction is at equilibrium. A reaction is at equilibrium, and once the reaction is at equilibrium, there are dynamically equivalent, right, or equal. There are dynamically equivalent products as reactants, right? So that does not mean that the concentration of the product and the reactants are equal. It means that they are dynamically equal. It means if you take products out of the equation, the reaction is going to favor such that some of those products are formed more to maintain the balance. And once they're like that, the reaction is not going to favor any forward or reversible reaction. No more products or reactants are going to be formed. So this is pretty simple. And once again, you can also do a calculation where your equilibrium quotient is greater than where your reaction quotient or equilibrium quotient is greater than your equilibrium constant. Now once you find it like this, what this implies is that the reaction has passed equilibrium, has passed the equilibrium point. The equilibrium point. Now since the reaction has passed the equilibrium point, the reaction will shift, meaning since the reaction has passed the equilibrium point, there are more reactants. No, there are more products than reactants, right, in the system or the solution or whatever the reaction is. Now if there are more products than reactants, then the equilibrium will shift to the side where there is less stuff. So the equilibrium will shift left. Once the equilibrium shifts left, more products, more reactants, more reactants are going to be formed. So these are the things that we need to take into consideration or into an account when we do calculate for the equilibrium constant, the quotient of a reaction, the equilibrium quotient of a reaction. All right, now if you are tasked to calculate equilibrium of reactions, now equilibrium of reaction can take on so many forms. It is not only in molecular chemistry, it is in biochemistry. You can be asked to calculate equilibrium constants of a lot of things. Like there are things like KSP, K of water, like KEQ as we have here. There are a lot of this is of acid and bases, this is of water, this is for chemical equilibrium, this is also for partial pressures. There are a lot of things that equilibriums can take form of. But what you should take note of, or what we should know, that the equilibrium constant, it does not matter the entity you are calculating it in, is always the concentration of the products, right? The concentration of the products. Now if they have stoichiometry coefficients in a reaction, or if you are giving the stoichiometry coefficient, it will be the concentration of the product to their stoichiometry coefficient divided by that of the reactants, right, to also their stoichiometry coefficients. You know this general thing, and you should be fairly fine to do equilibrium calculations. And one thing that you should also take note of is that these calculations that you are going to make, right, always occur at equilibrium when you are calculating equilibrium constants. If the reaction is not at equilibrium, then we're talking about QCs, which can also take form of many things, like how far we are away from the equilibrium point of that thing, right? So just take note of these generalities, solve more examples, and then you should be all fine fairly. Now from here, we are going to move to what we call the Le Chatelier's principle. Le Châtelier. As I once again, I am not a French person, so please pardon my French. All right, so let's move on to the next and the last topic under this chapter, the Le Châtelier's principle. Now, I am not a French speaker, so I might be butchering the name. Could be Le Châtelier. I have no clue how it is said, but go on with me. Le Châtelier's principle. Now, Le Châtelier's principle was a French chemist and a physicist, and he discovered something. Not really discovered, I know. I mean, back those it was a big deal, but today it's kind of a common sense, right? What he discovered was that if stress is applied to a system at equilibrium, right, the system or the equilibrium will shift to whichever direction to get rid of the stress. This is basic thing. If you stretch an elastic band, that means you apply stress to that elastic band. If you release that elastic band, it will come back to normal to alleviate that stress. It happens everywhere in everyday life. So that is what Le Chatelier's principle states, that if stress is applied to a system, shift or the equilibrium will shift to get rid of the stress. And then this stress here, if I say stress here, what I mean is not like stress as in our layman meaning of stress. Stress here could take the form of concentration, could take the form of pressure slash volume, could take the form of temperature, could take the form of enzymatic activities. It could take the form of increasing surface area of a reaction. It could take the form of anything. That is the stress we are talking about over here. So now, let's go into what if we alter any of these stresses, what will happen to the system at equilibrium, right? Let's say we have like our our generic equation over here. Cc plus dd over here. If we increase the concentration of the reactants over here, right, it means we've added stress to this part of the reactant or to this side of the equation. So the equation is going to the system is going to shift to get rid of the concentration we just added, meaning the system is going to shift towards this side so that more of the products are being produced to get rid of the concentration we added. Same way that if we do add the concentration over here to the products, the system is going to shift towards the reactant so that we get rid of the concentration that we did add because we added more concentration. Yeah, so we add the concentration to the products over here. The system would shift just so that we can produce more of these products to get rid of whatever we did add over here. Pretty straightforward. So that is concentration for you. Now for pressure, and this applies in gases. If we have a vessel and we put pressure in it, the system is going to shift just so that there are less pressure. And for gases, what you have to know is that although you might add pressure to it, but the system will shift in such a way that it goes to wherever there is less total number of moles. So let's say if these were all gases, right? If these were all gases, and since they are all gases, I apply pressure because that means they are in a vessel. If these are all gases, it's going to be in one vessel like this. Both A, B, C, and D are all going to be in this vessel like this. So I cannot selectively apply pressure to just A or B. If I apply pressure to this system, it's the entire system that I apply the pressure on. So what is the system going to do to overcome this pressure? The system is going to shift going to shift to wherever there are smaller number of moles. Let's say this was supposed to be a reaction like say 2, 1, 3, 2 over here. Let's say this is balanced. The total number of moles over here is 3, and the total number of moles over here is 5. So if I do apply pressure to this system, it's going to shift to where there is less moles, which is 3, right? So that the system would be balanced in order to distribute the pressure that is on the system more important. The same thing applies to the volume. If I increase the volume of this container over here, like this was the volume, and now all of a sudden, boom, I have increased the volume of the container. Same thing. The system is going to shift towards where there are less moles, not where there are less volume, where there are less moles, so that the system will equally distribute. So that is for pressure for you. Now on temperature, this is where it gets a little bit tricky, but stay with me over here. Let's say I have a system of that reaction and I apply the temperature to the system. Now you're going to say that the reaction is going to go in a favor or wherever there is less temperature. But no, that is going to determine on the specific type of reaction that I am encountering. Now if I'm encountering an endothermic reaction, endothermic reaction means the system takes up heat. It takes up heat as reactant, right? So if the system takes up heat as a reactant in an endothermic reaction and apply more heat, means I am applying more reactant. So the system is going to shift to produce more product. That means to get rid of the heat that I just applied. That is the tricky part over here. Now, if the system is exothermic, right? Exothermic means it gives out heat. The system already gives out heat to the environment. And I do apply more heat. It means I am applying more products. It means I'm applying more products into the system. Let's say, for instance, let's give us like a reaction whereby I produce heat as a result, right? Say sodium, right, reacts with an acid, HCl, and it's going to give me sodium chloride plus water with a release of heat. I do add temperature to this system. If I apply more heat to this system, I'm applying more product to the system. So if I'm applying more product to the system, the reaction is going to shift just so that I can use the product that have been applied to the system. So the equilibrium for this system will shift to the left. Same thing over here. Let's say I have say magnesium oxide. Like I'm burning magnesium oxide to produce magnesium plus oxygen gas, right? To produce magnesium plus oxygen gas. Now in this system, it's like you see the tip of a matchstick is a compound similar to magnesium oxide. Now I need to apply heat, like strike the matches, and heat will be applied. So if I strike the matches and heat gets applied to this system, means I added heat to this system over here. That means I've added reactant to the system. If I add reactant to the system, it's going to shift in such a way that it will get rid of the heat. So in this way, the equilibrium will shift to the right for me to produce more magnesium and then oxygen. So that is just the Le Châtelier's principle over here and how it affects various systems. And by so doing, this brings an end to the chapter 7 of the MCAT chemistry review. Now I might have skipped a little bit of nuance. If you follow my TikTok channel, we're going to be solving more work examples over there so that you know how to tackle such equations or such problems when you find them you meet them on the MCAT. Once again, my name is Richard. Thank you for watching.